Welcome back to the lab. Welcome back to EE for everyone. Today we are going to make a big decision. What type of compensation network, what type of compensator is going to be right for the electronic load project? There are three major contenders in my mind: a type 2 compensator, a type 3 compensator, and PID. So what do I think is going to be best for this design? Let's find out. A few videos back, you might remember we started using a PID compensator for some LT Spice simulations. It was pretty cool, and you might have been wondering, why did I start with PID? Why didn't I start with something else? And, well, they're used pretty much everywhere, and that's for a reason. They're pretty flexible, and in my opinion, PID compensators tend to have less dependency on the plant. Like, it's easier to make a stable loop regardless of what you're controlling with PID compared to a type 2 or type 3 compensator. A type 2 or type 3 compensator is much more closely coupled to the load or the plant of the control system, the output. I said enough generalizations there that I'm almost certain to have misspoken or been wrong at least once. So let's just move on past that and focus on type 1, type 2, and type 3 compensators. That might expose more of what I was trying to get at. These are three circuits that only use one op-amp to do the full control, and they can be built using either an op-amp or a transconductance amplifier. They're similar things, but one of them has a current output and the other one has a voltage output. That will change the general shape of the circuit, the general form of the circuit, but not the components or the function. It's basically whether or not they're hanging off to ground or in series in a loop, but we'll get to that in a moment. You should see some pictures flying up on screen. Coming back to that, though, a type 1 compensator is a simple integrator. We've talked about integrators before, nothing special. And type 2 compensators adds a few components on top of that feedback loop of a traditional integrator. And basically what that does is it gives our controller a different transient response. It causes it to respond differently. Now, why is that important? Why does that different transient response matter? One, because it'll help it to respond a little faster and behave a little better, which is good. But the reason why I'm being such a stickler about this, talking about it in terms of control systems, is because the gain and the phase of the frequency response of our controller will be convolved or combined with the plant or load, its frequency, or its gain and phase response in the frequency domain. And then after that, the stability of the system is determined based on the combination of the controller and the load, the compensator and the plant. And I don't know what our plant's going to be. I know we've got a FET. And then that FET takes something and dumps it through our shunt resistor. We measure the current through that shunt. A part of the plant we know very well, right? That's our transistor. That's our little ohmic shunt. But I don't know what we're connecting to it, and that starts to make me a little nervous, right? I don't know if it's going to be highly capacitive. I don't know if it's going to be inductive. I don't know what we're connecting, and that is a little scary. It's a little scary for type 2 or type 3 compensators, and I've used them before quite often. I'm sure you have too. It's basically the same type of compensator that's used in every DC to DC or switch mode power supply. And the reason why is because you know the plant really well. You can usually assume that what's electrically close to your switch mode power supply is your output inductor and the output capacitance, and everything else is electrically far away enough that it doesn't really matter for your control loop. At least that's generally what I've seen assumed. We can't make that assumption here. We don't have an output inductor and output capacitance. So perhaps I could find a way to apply that theory and make something that would be stable for all loads and do some intense analysis, but it seems a little complicated. It seems like forcing something to do what it was not designed to do. Right? PID is used often for motion control. It's used often, honestly, even for control loops for power supply. It's used everywhere. And I think there's a reason for that. But anyways, before we move on to start talking about PID again, I just want to talk about type 3 compensator And basically it's a type 2 with an added phase boost in the feedback network. It adds a feed-forward capacitor, in other words, into the control loop. It provides a little phase boost that generally makes it a little more aggressive in transient load conditions, which is usually preferred. It adds an extra pole and 0 in the gain plot and, of course, the phase plot. But if you want a more detailed explanation about type 2, type 3 compensators, seriously, check out the app note linked in the description because it's awesome. Like, this app note from TI is one of the best I have ever seen on type 2 and type 3 compensators. I think it does a really good job of walking through what each of the components does, how to physically construct them with op amps or transconductance amplifiers. It's pretty awesome. So definitely check it out. Kind of an aside, like, TI, thanks for making this publicly available. Most people wouldn't. I appreciate the fact that you just build this cool information and drop it on the internet. Like, that's really cool. Thanks. For better or worse, I ended up back where we started with the PID compensator, and I think that's okay. But before we wrap this all up, I need to make sure that our coefficients make sense. So I didn't just want to throw any old compensator down and say, hey, look, it's a control loop. So I just want to take a moment to show you where that testing got to. It really wasn't very exciting, right? It's a little bit of math, and then it was looking at the transient response, and then it was iteratively tuning it, shaping it up to where I needed it to be. Yeah. So this is where the loop ended up. You're seeing a load step where we slowly ramp down the output current and then step it up as fast as we can. And just want you to notice the practically 0 overshoot. Like, that's pretty cool, combined with the very reasonable rise time. Like, that comes up very quickly, it doesn't overshoot, looks pretty solid. The glitch is handled very well, and let's compare that to where the loop was before. So I'm running the same response here, and yikes, it looks like we made some big improvements with our little bit of effort. Notice how the glitch on the output is much more significant. It actually derails our output current waveform for a while. There's simply more overshoot and ringing, and the settling time is way longer than our tuned version. So, yep, that's the difference between just throwing components in an LT-Spice sim because the number's easy to type in and actually tuning something and designing it. Turns out designing it works better. So there you go. I'm sure nobody's surprised. Okay. Before we move on, I just want to fade back and forth between the two. Like, there's something about a control system working well that just... Let's talk about some of the key differences that I made between those two. And the D term was reduced, the I term was increased, P was left unchanged, and that's really it. That's all that was changed between those two transient responses. So a very subtle change can have a pretty big impact on how something works. I had some fun today walking through kind of my mental journey, if you would, getting back to some of that, good talking head rambling. Yes, that's good. But if you're like me, you're probably feeling a little gypped because you probably walked into this video expecting that we teach you how to do this yourself, teach you everything you would need to know to tune a PID compensator, pick the right type of compensation network for your application. But there's a really good reason why we didn't get to all that today. A really good reason. That would be talking through 2 or 3 semesters worth of control systems lectures, and this is a 10-minute video. Like, I'm trying to do the best that I can with the time we've got, but you just can't cover 3 semesters in 10 minutes. There's a lot of background information, a lot of theory that you need to understand before you... It's hard. It's hard to boil something like that down into this kind of density. But this conversation doesn't need to end, so please, in the comments, if you've got great material, if you've got some supplemental information, your favorite textbook, whatever it is that helped you to learn more about control systems, why don't you drop that in the comments so other people can see and learn from it? Because, hey, that's what we're here for, right? Links will probably get moved to a general spam bucket, but I can manually review and release those back into the comment section. So don't hesitate. I'm going to volunteer myself to moderate that. So just drop links, drop names, whatever you need to do, and I'll sort through it and figure it out. So yes, I want to see that comment section blow up with some good control systems information. That said, if you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we will be selecting our microcontroller and making a strategy for how we're going to prototype. Though some of you might not have been around for that long, but we don't really have a shop right now. So this is going to put us in a very interesting set of circumstances, but let's see what we can do. I can't wait for that. But most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for everyone, and thank you for staying till the end. Bye.